You was writing paragraphs. You
Well,
arguing?
that is.
Ooh.
You was.
I
I
know
see you
you
going
see
off.
me
I see all those blue
here.
facts.
No, exactly.
Do I look good, my dear?
You're being recorded right now.
They don't know my name.
Jordan Overton.
Jordan Overton.
Kate Torres. Laura Laurent.
Anyways. Okay, so we have learned two properties of exponents so far. The first day that we started back on break, we worked on the multiplication property. We also called it the product property. We knew that if you're multiplying numbers with the same base, that you can add the exponents together. We really did break everything out just to see why we're able to add together, and I'm a big fan of breaking everything out so you could see it. On Wednesday, we learned the division property of exponents, where we noticed that we could break everything out and find big ones. We could represent those big ones, and we didn't need to show them because I don't have to show if something's being multiplied by 1. That was how we were able to simplify using the division property of exponents. Today, we're going to simplify something like that. How would you say that number? If someone were to say it, how would you explain that?
3 squared to the third.
3 squared to the 4th power. So what am I doing?
You're multiplying 3 to the 2nd power by itself 4 times.
I'm going to multiply 3 to the 2nd power by itself 4 times. So this is going to be the example that we work with here. So it's almost like in this situation, 3 to the 2nd is like the base. And I'm going to raise it to the 4th power, that exponent. So just like you said, 3 to the 2nd power times itself 4 times. So 3 squared, multiplied as a factor 4 times. Another way you can see this, depending on how you look at these numbers, you can look at this as the product of 4 powers, each with the same base and same exponent. So the same number 4 times, that number is 3 squared. If I were to break that out, how would I break it out if we had 3 squared to the 4th power?
3 squared times 3 squared.
Yeah, you can break that out. 3 squared times 3 squared times 3 squared times 3 squared. Does that make sense? That we're actually taking that number, everything inside the parentheses, and we're multiplying it by itself 4 times.
Yes.
Yeah, so show that breakout in your notes if you're using that example. Is that fully expanded?
No.
What else could I do? Could I rewrite or break any of those numbers out further?
Yes.
Which numbers?
3 squared can become 3 times 3.
Yeah, 3 squared is actually 3 times 3.
Times 3 times
So this also is 3 times 3
times 3.
times 3 times 3.
Times
After this first layer, when we broke out from this term to that first breakout where we had 3 squared times 3 squared times 3 squared times 3 squared, what property does this look like? What property does this look like? What property, if you just saw this as your expression, what does that look like?
Multiplication.
Yeah, it looks like the product property. It looks like something that we've already learned. Okay, so we knew based on the multiplication property or product property that we could break everything out. So now, based on this breakout, we had 3 squared times 3 squared times 3 squared times 3 squared. We knew that we could rewrite that as 3 times 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 3. What does that simplify to? What am I really multiplying?
3 times itself 8 times.
3 times itself 8 times. So if I simplify this, it does simplify to 3 to the 8th. Now, as you look at this, think back to last week when we were learning the other 2 properties that we know already. There was a rule for the product property. If I was multiplying with the same base, I could add the exponents. There was a rule for the division property. If I had the same base, I could subtract the exponents. So what rule might you come up with now based on the example that we went through? If I'm multiplying a number and raising it to a power, what does it look like we could do?
You're multiplying the exponents.
Yeah, we could actually multiply the exponents. This is called the power of a power property. So you may also see it power to a power.
Power to a power property.
power of a power, and really it's an exponent being raised to another exponent. So write this down in your notebook. This will be the third property, the third rule that we're learning, the power of a power property. To find a power of power, you can multiply the exponents. So your example here, in addition to the one that you already have, right, which you have 3 squared to the third power. Another example here, and this is an example where your base is a variable and not a number. A squared raised to the third power is really the same thing as a squared times a squared times a squared. You have 3 terms here because your exponent is a 3. And then you could break it out even further if you needed to. A squared is a times a times a times a. So you really have a to the 6. Now, just like last week, we don't want to focus only on a rule, because now what's going to start to happen, and it's very natural, is that if you're only focusing on the rule, it's so easy to make some little mistakes. You're going to see an example in a few minutes of why I would recommend starting with the breakout until you get really, really comfortable, because it can get a little tricky if you're focusing just on a rule. So make sure you have this definition and the example that we went through, the 3 squared raised to the third, and also a squared to the third. Okay. If any of you looked at the assignment on the Google Classroom from Thursday, those practice problems, you might have seen problems like this, where there's some parentheses, there's brackets with exponents inside and outside. After today, you'll be able to do those practice problems. So I would encourage you at home to take a look at that assignment on the Google Classroom and try the power of a power examples, just to get that extra practice in. Does anyone need more time to write this? So if we had 5/8 to the 6, using that same relationship, what would the simplified expression be if you wanted to use the rule for a power of a power? Yeah, 5 to the 48th. I could multiply 8 times 6. If I wanted to break it out, you really have 5 to the 8th how many times?
6 times.
6 times. So take a look. If you did the rule in the beginning and actually applied that property, you would get 48. But if you broke it out here, at this level, you actually have the product property, where we know if we multiply with the same base, I could just add all of the exponents. So 8 plus 8 plus 8 plus 8 plus 8 plus 8 is 48. It's another way you could have gotten 5 to the 48th power. How about 953 to the 7th raised to the 3rd?
Whoa.
953 to the 21st power.
Yeah, again, it doesn't really require an additional calculation. We're not looking to necessarily raise that base to the power and calculate it out. Right now, we're just working on simplifying. There's another way that you might see the power to a power. Yes?
Like this in scientific notation, like, can you like clarify that? Because I'm getting like what's the difference?
Right now, we're only working on the properties of exponents, and next week we're going to start to work with scientific
But what is
notation.
it? Like, what's the difference?
Writing a number in scientific notation allows you to take extremely large or extremely small numbers and represent them in one way. So again, this is just the rule for power to a power. We are able to, if we're raising an exponent to another power, we're able to multiply them as long as n isn't 0, right? Because 0 to any power is just 0, so that's going to change some things. So there's another example here that is the same property, but a little bit different. So what do we notice about this example? The bases are different. And that's very, very, very different than all the other properties we've been working for, because when you wrote down the rules for the product and the division property, the key was that any of those things that you did, whether you added the exponents or subtracted the exponents, the base had to be the same. But right now, these two numbers, these terms, they don't have the same base. Their bases are different. What do you notice about their exponents? Their exponents are the same. So let's see if we can do something here. Could I represent this term with no exponents? What would it look like if I broke it out?
3 times 2 times 2.
Is that the same thing? Is the value changed in any way? No. So let's tap back to some previous information that you've learned in previous years. The associative property and the commutative property. Anyone remember what they are?
For commutative, you can switch them around.
For the commutative property, I can change the order of what type of problem? Addition or multiplication. Yeah. 5 plus 3 is the same as 3 plus 5. 10 times 6 is the same as 6 times 10. I can change the order if I'm multiplying or adding. Does anyone remember the associative property? Yeah, we can actually regroup the numbers. Perfect. So could I rewrite this expression into groups of 2 times 4? Like, could I rewrite these numbers?
Yeah.
Yeah, how can I rewrite? If I wanted to show the product of 2 times 4, how can I rewrite that?
2 times 4. 2 times 4 times 2 times 4.
Are those the same?
Yes.
Yes, they are. Did I change the value in any way? No. The commutative property tells me I can change the order. And right now, we're going to actually do something with the associative property. How many groups of 2 times 4 am I multiplying if I had this?
How many groups of
3.
How many groups of 2 times 4 am I multiplying here?
3?
Could I group them?
Yes.
Would that be 2 times 4?
Very good. 2 to the third times 4 to the third is actually the same as 2 times 4 to what exponent? To the third. Could I simplify what's in the parentheses?
Yes.
What is that?
8. I'm impressed. This is interesting.
So this is another way that you could actually simplify an expression, but this is when we have power of powers, different bases, same exponent. So if you have different bases, but the same exponent, you could simplify it in this way. The key here, and they use the variables to show you that A and B would be a different base, but that the n is the same number for this example. So if you had different bases and the same exponent, you could actually represent it using the associative property and create groups. Both examples are helpful. The 2 to the third and 4 to the third might be a little bit clearer for you to see how that actually happened. And again, we broke it out. 2 times 2 times 2 times 4 times 4 times 4. Using the commutative property, we knew that we can move the numbers around and not change the value. And then using the associative property, we can create the groups. And that actually gives us 2 times 4, which is raised to the third power. And if you had 2 times 4 like that inside the parentheses, it is completely acceptable to represent that as 8. You can represent that in its most simplified state as 8 to the third. You really aren't, you're not expected to calculate that out right now. If you felt really excited and wanted to, you could, but not necessary. Right now, we're just focusing on simplifying.
5 and 12.
Now, earlier I was saying how we don't want to just focus on rules because rules can get us a little tripped up if we mix them up. Last week when we talked about these rules, the example I used was how many of us add a negative and somehow end up with a positive, messing up the rule for multiplying negatives compared to just adding together 2 negatives. And that's a common mistake. So those types of mistakes carry over when we're dealing with the property of exponents. When we're dealing with power of powers or power to a power, that mistake somewhat comes back. And this is the last thing that we want to take a look at here. What am I multiplying? If you wanted one more example just to show common errors, this would be a really great one for you. What am I multiplying here?
3 times
X
times
X times X to the third.
So 3x to the third.
Wait, what?
3 times.
Wait, are we writing it out? Like,
If we wanted to break it out, what would I be multiplying?
3 times x times x times x times. Wait.
Wait, 3 times
No.
x cubed times 4 times.
No, yeah.
Right, okay, so I'm gonna backtrack. We are eventually gonna get here, but at its most basic level, we're multiplying 3x cubed 4 times. Can I break out 3x cubed?
Yeah.
Yes. What is that?
3 times x times x times x.
Okay, so that's 3x cubed broken out. So I'll just break out the other ones. Okay, so if I wanted to simplify, let's put it together. What do I have?
Have 12.
I am multiplying x by itself how many times? 12 times. There's 3, 6, 9, and 12. How can I represent multiplying x by itself 12 times? X to the 12. Okay, so now I'm just going to cross these out. What's left? I see the number 3 4 times. So what operation is this? Multiplying. So what am I multiplying?
3 times 3.
Okay, so 3 times 3 times 3 times 3. So what is that number? What's 3 times 3? 9. What's 9 times 3?
27.
What's 27 times 3?
81.
Only person.
So let me show you the most common wrong answer for this one, okay? The most common wrong answer is this. Why do you think this is the most common wrong answer?
I don't even know how they got the 12x. Where did they get that?
Multiplying 3 by itself 4 times, they multiply 3 times 4.
Yeah, instead of multiplying 3 times itself 4 times, the most common wrong answer would be to multiply 3 times 4. And the reason this happens, hi, no, come on in.
Just need to see Jordan for 2
Yeah.
seconds.
The reason this happens, think back to the rule, the property that you just wrote down. If we know that we have a number raised to another power, we could just multiply. What happens is people see this and they say, okay, so I'm going to multiply this times 4 and this times 4. But it's different because you're not actually multiplying that coefficient times 4, you're raising it to the 4th power. Everything in here is being raised to the 4th power. So what you're really doing, 3 to the 4th power times x cubed to the 4th power. And again, this is where the rules can get confusing. That's why, when in doubt, break it out. If you break out this expression and you see that you have a 3 times a 3 times a 3 times a 3, I think and I hope that you'd be less likely to just say that you have 12 because everything at this level is multiplication. So I hope that if you saw it broken out, you would not think that you're just adding when in fact this entire expression shows multiplication. You alright? Okay. You will see a lot of these power to a power, power of a power. For those of you, again, that saw that Google Classroom assignment, you saw a lot of parentheses, a lot of brackets, and you're going to see a lot of other examples like that as we move forward. Now, we're still in the process of learning the properties individually. On Wednesday, you'll start to see them together. Especially tomorrow's like the one that pulls it all together. When you start to see those two properties, that's when you'll see multiple. Does anyone have questions about how we get from 3x cubed to the 4th broken out to 81x to the 12th? Go ahead.
3 to the 4th power.
Yeah. Yep. So the reason I wrote this, everything in here, everything in this parentheses is being raised to the 4th power. So if I wanted to break it up, I could. By breaking it out this way, you are actually showing that you're doing 3 to the 4th power. So you have 3, 3, 3, and 3. And then x cubed, which I crossed out, but x cubed times x cubed times x cubed times x cubed. Whether you go to this level, which I don't know if you'd naturally go here, you would probably break it out first and see the multiplication from there. So don't necessarily worry about that breakout. The goal is that you know that it shouldn't be 3 times 4. And it'll happen. Again, this is the most common wrong answer, 12x to the 12th, because If you get that, then you didn't multiply the 3 to the 4th, you just multiplied it by 4. So I encourage you, especially in the early stages when you're just getting comfortable with these properties, to break it out and then see what it is that you're actually multiplying before simplifying it back together. Okay, so I'm going to pause this.
Or right into